This is problem number 5, which says that a hemispherical surface with radius r, I'll draw that a little bit better, in a uniform electric field E, let's see, and the axis is parallel to the electric field. Calculate the flux through the surface. Now, this hemisphere is not necessarily a closed surface. I'm going to draw the axis here in green. It looks like that. Now, we have a ring, an open ring on this side, and then a closed surface. It's not really closed, but it's a solid surface on the round side, but the circular side is open, which makes this simpler. Throwing down a couple of equations, area of a circle equals pi r squared, and the area of a sphere is 4 pi r squared, and we will be dealing with half of that. So the area of a hemisphere, outside of the hemisphere obviously, will be 2 pi r squared. We might not actually need that, but I'm throwing it up there anyway. And then flux is the integral of the electric field dotted with the area component. That might be a little bit hard to see. Sorry about that. Also, this integral of the electric field dotted with the area component is equal to the charge enclosed over epsilon naught. Now, going back here, if we imagine that we close the surface, and there is no charge inside the surface, any flux through the circle will be negative of the flux outside of the hemisphere. So, flux of the circle plus flux of the hemisphere equals 0. And because I'm going to draw a couple of normal vectors on here, assuming that this would be a closed surface. So the dot product of the electric field and the normal of the circle would be negative. Well, this would be positive, so I'm going to write it that way. So the flux through a hemisphere will be negative of the flux through the circle. Assuming a closed surface, and if we're just looking at how much is going through the hemisphere, then we can calculate that, drop that, and that's our answer. So this one is easier to solve. So we have the flux of a circle will be integral of the electric field dotted with the area component, which when you take the integral of this will give you E times A. And we have up here, area of a circle is pi r squared. So this will be E times pi r squared. And that is the flux through the circle. If we pull that over here, area, or the flux through the hemisphere will just be negative the flux through the circle, which is negative. Actually, I take that back. This is already negative because they are anti-parallel to each other. So we have negative E pi r squared. So the flux through the hemisphere is just E times pi r squared. Simple as that.